Okay, one final example. Now, I will say that in the final assessment, I do think that the differentiation might be a bit more complicated than this. So what I got, for a light beam of a particular length, simply supported under load varying from 4 to 16.48, it can be shown that the bending moment in kilonewton meters at x equals 6 meters is given by this. So just to be clear, you got the beam. It's got a length approximately 6.24, and we're looking at 6 here, and there's just a formula here, but A and B are actual numbers. So this is a particular number. I mean, we could bang in the numbers there. 216 by A is 1/3 minus 72 plus 6 by 280 over 11. So the bending moment at 6 here is equal to 96 over 11, which for argument's sake is approximately 8.727. And it should be measured in kilonewton meters. Okay, that's all I'm saying. But those numbers that pop out, say, you try and solve this, you bang in the numbers. These A and B are these numbers that come out. Okay, explain why if A and B are rounded to 2 decimal places, that the rounding errors delta A and delta B are both equal to 0.005. Use differentials to estimate the rounding error in M caused by the rounding errors in A and B. So if you, instead of using 1/3 and this, if you round these, so use like 0.33 and whatever this is, estimate the error in the calculation of this. Calculate the exact bending moment. Well, we've done that. It's 96 over 11. And then calculate the approximate bending moment using these things. And let's look at the difference. Okay, that's all we're looking at here. Okay, so when rounding to 2 decimal places, the largest error is 0.005 to 0.01. So this is, what's this kind of saying? So in general, for example, if A is equal to, or is approximated, say, to be 1, or no, let's say if A is in between 0.995 and 1.005. If A is in between them and you're rounding to 2 decimal places, so this will round to 1. And the biggest difference between all these true values in this approximation, the biggest difference is between these two, which is 0.005. Okay, that's that. Use differentials to estimate the rounding error caused by the rounding errors in A and B. So this would be if you use 0.33 and 23.45. Estimate the rounding error in the calculation of this 96 over 11. So here we go. Using this, so this is equal to, so the derivative with respect to A, so differentiate this partially with respect to A. So fixed constants, differentiate term by term. So fix the minus 216. The derivative of A with respect to A is 1. And with respect to A, so A is changing, but everything else, in particular B, is fixed. Minus 72 and 6b are constants, so the derivative of them is 0. There's an absolute value around this, times the error in A here, which is 0.005, plus differentiate this with respect to B. Now, differentiating with respect to B, A is fixed, so this will be a constant, this will be a constant, so the derivative of both of those is 0. Plus fix the constant 6, and the derivative of B respect to B is 1, times 0.005. So this will be equal to, let's calculate this, now it's minus 216, but with an absolute value is plus 216 by 0.005 plus 6 by 0.005 is equal to 1.11. But we need to approximate that because it's an error to one significant figure, 1, and the units of bending moment is kilonewton meters. So here, like, we can kind of look ahead we get a fair bit of error here. Like, it's about 9, and we have an error of up to 1 by rounding, just by rounding like that. So be careful. So question 3, calculate the exact bending moment. So this would be m of 1/3 280 over 11. I think we did this already, I'll just double check. So minus 216 by 1/3, minus 72, plus 6 by b is 280 over 11. This is a fraction, 96 over 11, and I'm going to present this correct to 4 significant figures. 8.727 kilonewton meters. And the other question is calculate the approximate bending moment using 1/3, instead of using 1/3, using 0.33, and instead of using this, use 25.45. So this would be the bending moment using the rounded values, 0.33 and 25.45. We get, so instead of 1/3, 0.33, and instead of this number here, we use 25.45. Yeah, I can't delete that one, let's put a 1 there. So I get 471 over 50, which is equal to 9.42. And look at the difference between them. Look at the difference between them, big error. It's of the order of 1. That's rough. Now this is rough because it doesn't capture it exactly. It's actually slightly less than 1, but you get the idea. So in general here, what I'll be looking for is you put your measurement plus or minus your error. So your measurement here would be using the rounded values, 9.42. But here, look at the 1, you should round it to nearest 1. So round this to nearest 1. So what you could see here is that the m is equal to 9 plus or minus 1 kilonewton meters, and notice that it does capture the 8.727, which is a good thing. So there's plenty of exercises for you to try. I haven't yet designed the assessment, so I really can't say anything about that.